Hello class, this is a video tutorial on independent events. Two events, any two events, A and B, are considered independent of one another if the probability of one event occurring is the same regardless of whether the other had occurred before it. That seems a bit like a mouthful, but let's take a look at a simple example of this. If a regular coin lands heads 2 times in a row, the probability of heads in the next flip is still 1 in 2. Intuitively, we understand this as the result of one coin flip has no effect on other coin flips. This understanding extends to other chance experiments such as dice and spinners. A simple example of, well, another extreme example of this is if a regular coin lands 99 times in a row as heads, the probability of heads is still 1/2, no matter if it was 99 times in a row. Now, that is the intuitive idea of this, but you'll see that with more complex events, we need to define this and prove this mathematically. And how we do this is this idea. Two events, A and B, are independent if the probability of A given B is equal to the probability of B. Otherwise, A and B are dependent. So take a look at this idea. It says the probability, so it's if the probability of one event occurring is the same regardless of whether the other had occurred before it. So if the condition of B gives you the same probability as A occurring on its own, they are independent. Let's take a look at an example of this. Let's think about these two ideas. A is the heads lands on the third flip. I've actually already constructed a multi-stage experiment here, or a tree diagram, and I've already shown the outcomes where heads occurs in the third flip. 1, 2, 3, and 4. So there are 4 things out of a total of 1, 2, 3, 4, 5, 6, 7, 8. 4 in 8. Well, that is going to be 1/2. The probability of B is heads is happening in the first 2 flips. Well, there's only 2 branches of this. Heads, heads. So take a look. There are 2 branches. 1, 2. There are 2 branches here. So 2 out of 8. That's a quarter. And the intersection of both, meaning the intersection is third flip is heads, and the first 2 are heads. Well, there's only one thing here where the first 2 flips are heads and the third flip is heads. So it's 1 in 8. Now let's take a look at the formula. We've used this before. The probability of A given B, well, A given B, remember we need to figure out the probability of B in the denominator. Well, we can see that there are 2 things in our denominator. Because remember, B is the condition. Which things give us 2 heads? Well, these 2, 1 and 2. So our denominator is 2 things. And A is heads on the third flip. So now of the condition, so these 2, which things have heads as the third flip? Well, one thing, 1. Now notice, look, the probability of A given B is equal to the probability of A. Half is A given B, and half is the probability of A. So we can say that, that these 2 are independent. Okay, so now this formula can be used to test for independence in more complex scenarios. So let's take a look at a scenario here. So In this case, it's back to our jumpers and blazers like we did in the previous one. In this case, we only have a class of 20. But look, I've changed the numbers here such that, well, you'll see in a moment here. So let's fill in this Venn diagram and figure out whether jumpers and blazers are or aren't independent. So in this case, let's fill these out. Neither here should be 10 on the outside. We can see that there should be a total of 10 remaining, because 10 minus 10, there should be 10 people left in this circle. But 6 plus 5 is a total of 11, which tells us that one person is here in the center. So in this case, take a look. We can figure out now this number here is 6, take away 1, going to be 5. And this number here is going to be 5, take away 1, which is 4. So now to test for independence, let's take a look at the probability of A. The probability of A is nice and easy. That's 6 out of a total of 20, which we can simplify into 3 in 10. Now the probability of A, or sorry, this should be J, probability of J. In this case, the probability of J given blazers. Take a look. Remember now to do this, we limit our denominator to blazers. So in this case, how many things are in the group of blazers? In this case, there are 5. So 5 is our denominator. Now, of the things in this group, how many of the 5 are still part of the other group J? In this case, it's going to be 1. Now, in this instance, take a look. The probability of J does not equal the probability of J given B. Therefore, these are dependent. Now, intuitively, it obviously makes sense in this case that if we limit the number of people, in this case, blazers, it feels like the number of people with jumpers as well should be smaller, therefore dependent. But now let's take a look at this example here. So similar idea. We start with the obvious piece of info. So 12 goes on the outside here, which gives us a remainder of 8. So 20 minus 12, there should be 8 people inside these circles. But 5 plus 4 gives us 9, which should be 8, which tells us there's one person in the center. Now from here, we can figure out the jumpers is 5 take away 1, it's 4. And in this one here is going to be 4 take away 1, which is 3. Now let's take a look at this scenario. The probability of J. Well, that's nice and simple. There are 5 people with jumpers out of a total of 20. So 5 in 20 is going to be 1 in 4. Now the probability of J given B, remember, the conditional probability, we look at the condition, B. There are a total of 4 people in that group. Now, of this group, which ones are still part of J? Well, there's one person here, 1 in 4. Now, as you can see, the probability of J equals the probability of J given B. Therefore, these are independent events. And that is the general idea. So as you can see, even though we have this intuitive understanding that events are definitely independent, such as coins and dice and spinners, there are some instances like this one with jumpers and blazers where we can't necessarily know whether they are independent or dependent unless we go through this formula. So remember, two events are independent if A given B is the exact same as if it was just the probability of A. So I hope has given you an insight into the idea of independence and dependence. And hope to see you in the next video where we cover some more ideas here. Hope to see you in the next video and best of luck.